Okay, in this question we have to find peak value of fundamental flux density wave in air gap. Okay, this is a star connected cylindrical rotor alternator which develops an open circuit EMF of 415 volts. Okay, now let us calculate first how many series turns per phase are there. Okay, series turns per phase. Okay, this is equal to, I will represent it as n phase, 36 into 4 by 3, which is equal to 48. Okay, the armature has 36 slots with 2-layer winding of full pitch coil with 4 turns each. Okay, so total number of conductors here is 36 into 4 per phase. This is a 3-phase machine, so by 3, which is equal to 48 series turns per phase are there. Okay, now number of slots per pole per phase is equal to, we will represent this with m is equal to 36 is the number of slots we have per pole. Is this is a 3-phase 6-pole machine, so 6 into per phase is 3. Okay, so m is equal to 2, 36 by 18. Now slot angular pitch, that is gamma. Slot angular pitch is equal to, gamma is equal to 180 by 6. Okay, which is equal to 30 degrees per slot. Now distribution factor KD is equal to sine m gamma by 2. Okay, m is 2, gamma is 30, so 60 by 2 by number of slots per pole per phase, which is equal to 2, that is m into sine gamma by 2. Okay, slot angular pitch is 30 degrees, so sine gamma by 2 is 30 by 2. Okay, we can find this one as 0.966 as the distribution factor, whereas coil span factor or pitch factor here is Kp is equal to 1. So what is winding factor? Winding factor Kw is equal to Kp into Kd, which is equal to 0.966. Okay, now EMF induced per phase in this cylindrical rotor alternator is 4.44 n phase phi times of Kw. Okay, from this we can find flux phi as 415 volts. He has given as open circuit EMF of 415 volts. Okay, divided by, since this is line voltage, we have to convert it into phase. E phase is 415 by root 3 into 4.44. Frequency is 50 hertz into 48 into 0.966. Okay, so we will get this as 0.0233 Webers. Okay, this is the value of flux. We have to find here fundamental flux density, that is V. Okay, but 5 is equal to, that is flux is equal to 4 by P times of fundamental flux density into L into R. Okay, from this, what is fundamental flux density value? P into 5 by 4 times of L into R, which is equal to 6 into 0.0233 divided by 4 into 0.4 into 0.09, which is equal to 0.971 Tesla is the answer. Option A is correct answer. 3-phase induction motor has the ratio of full load torque to maximum torque as 0.5. Okay, he has given torque full load to T max as 0.5. Okay, we know that this ratio is equal to 2 by slip full load by slip corresponds to maximum torque plus slip corresponds to maximum torque by slip full load. Okay, this is a formula for torque full load by torque maximum. Okay, so I will take S full load by, that is slip full load by, slip corresponds to maximum torque ratio as X. So what can I write this one? This I can write it as 2 by X plus 1 by X. Okay, I can find X value from this ratio as X is equal to 0.268. So option B is correct answer. kVA 50 Hz 200 by 400 volts transformer is taking 20 amperes and providing, that is producing 40 watts loss under short circuit. Okay, he has given copper losses, okay, under short circuit as 40 volts. In short circuit test we will find only copper losses, core losses is almost, we will take it as negligible. Okay, so whatever losses in under short circuit test, which is equal to copper losses, and current is given as 20 amperes. When excited from low voltage supply, calculate the full load copper losses. Whatever losses he has given, it is when transformer is excited from low voltage side. Okay, now what is full load current here? Full load current is equal to, transformer is rated as 10 kVA divided by 200 volts. Generally we will do short circuit on low voltage side. Okay, so this is 50 amperes. But what is the current? We are having here only 20 amperes. Okay, that is 20 by 50 into 100. This is equal to 40%. Whatever losses he has given, whatever losses he has performed under short circuit test is rated only for 40% of the total load current. Now what is full load copper losses here? Full load copper losses is equal to 50 by 20 whole square into 40, which is equal to 250 watts. So option A is correct answer. A DC source of 100 volt supply supplies a pure inductive load of 0.1 Henry. Okay, we have a thyristor here and there is pure inductive load L is equal to 0.1. This is a DC source of 100 volts. Okay, now latching current specified is 100 milliamperes. What is the minimum width of the gate pulse to ensure thyristor turn on? Okay, now whatever this voltage which is supplied from the source, it is going to be appeared across the load. Okay, that is V is equal to L into di by dt. So 100 is equal to L into di by dt. Okay, now I can write this one as 100 into dt is equal to L into di. Apply integrals on both sides. Okay, so this is 100 into t is equal to L into I. Okay, now from this, width of the pulse t is equal to L into I by 100. Okay, L value is given as 0.1 and latching current is 100 milliamperes. So 100 into 10 power minus 3 by 100, we will get it as 10 power minus 4, or we can write this one as 100 microseconds. So option D is the correct answer.